let's continue our discussion of primitive Pythagorean triples. So positive integer solutions to the equation a squared plus b squared equals c squared are called Pythagorean triples. We're denoting a triple as a tuple with a less than or equal to b less than or equal to c. A primitive triple is a Pythagorean triple that has a solution a, b, and c with no common factors other than 1. So we have a solution to the Diophantine equation, and none of the three pieces, a, b, or c, have any common factors other than 1. So we want to create different triples. And so we're looking for a pattern. Is there a pattern to these primitive Pythagorean triples? So the two triples that we are most used to from school days were 3, 4, 5 and 5, 12, 13. And so we notice that in both of these cases that the a values are odd and the other two values are separated by 1. So we have 4, 5, and we have 12, 13. So in both of these cases, a is odd, and c is equal to b plus 1. So the question is there a connection between a and b that's showing up in these two particular examples of primitive Pythagorean triples? So the question that we can look at in looking for this pattern with these two. Of course, looking for a pattern with two data points isn't always very useful because there might be something that shows up in 2 data points or 3 or a few data points that doesn't carry over. But this is what we're working with, and we're going to see if we can find a pattern that we can then extend to other situations. So if we look at the value a squared divided by 2, and then round that down, because a is an odd number, we square that, we get another odd number. We see that 9 is 3 squared, divide that by 2 and round it down, and we get 4. And 5, we square that, we get 25, divide that by 2 and round that down, and we get 12. So it looks like that this value of a squared divided by 2 is giving us a value for b, at least in these two data points. So when we round down a squared divided by 2, mathematically we can think of that as the floor function, so a squared divided by 2 and then the floor of that. Another way to get the same value is, since a is an odd number, then a squared minus 1 is even, and divide by 2, that gives the same answer in this case. So this is a mathematical approach, but how could we do this with Python? How can we get the integer round down of a squared divided by 2? So in that case, we have the integer division, and so we could use the integer division operator with a squared and 2. Okay, so this idea, at least in these two cases, we have odd choices for a, and we can then create the b from there, and then once we have the b, we can add 1 to that to give the c. So we want to know whether this pattern continues for other choices for other odd values of a. So if we set a to 7, then what happens? B would be 7 squared minus 1 divided by 2 using that approach. So we have 48 divided by 2, which is 24. And then C would be 1 more than that, is 25. And so the question is this a primitive Pythagorean triple? We look at those three numbers, 7, 24, 25, and we see they don't have anything in common in terms of common factors. So that part is okay, but the question is it actually Pythagorean? Is this a 7 squared plus 24 squared equals 25 squared? 7 squared is 49, 24 squared is 576. We add those together, we get 625, which is in fact 25 squared. So it continues at least this far for a equals 7. we have created another primitive Pythagorean triple. So, does this process always work? If we start with an odd number, can we always then create a primitive Pythagorean triple with this process? So, the idea here is we would have our odd number a, our rounded down version of a squared divided by 2, and then add 1 to that. And we're wondering whether that's always going to be a primitive triple. Now, we had the examples with odd values. We could look at what would happen with an even value for a as well. We didn't consider those because they weren't in our 2 initial data points. So we'll consider all these possibilities. So what if we start with an odd number of a equals 1? That's a smaller odd number. What happens? A would be 1. 1 squared is 1 divided by 2. The integer round down of that is 0. And then adding 1 to that is 1. So we would have 1, 0, 1, which does satisfy the equation, but it's not a Pythagorean triple because we said that the Pythagorean values have to be positive integers, and 0 is not positive, so it gives a solution to the equation, but not in the Pythagorean sense. But if a is greater than 1, then our numbers are going to work out for us. However, if a is even, there's a problem because a is an even number. You square that, you get another even number. Dividing by 2, an even number squared and divided by 2 still gives us an even answer. And so then we have an even number plus 1 as the answer for C. So we want to think about what happens if A and B are both even, and then C is 1 more than B. So let's look at other odd values of A. Is this always going to be a primitive Pythagorean triple for odd A bigger than 1? And so the question is, if we have these definitions for A, B, and C, does this always satisfy our Diophantine equation? Is A squared plus this value squared equal to the C value squared? And so to answer this, we're going to have to do some algebra. We have to expand the left-hand side and see whether it matches what happens on the right-hand side. So looking at the left-hand side, well, the a squared is here, and we have the a squared minus 1 all over 2 squared here. Expanding this second set of brackets here, the exponent 2 applies to the numerator and separately to the denominator. So the numerator becomes a squared minus 1 quantity squared, and the denominator is 2 squared or 4. So we have a squared plus this fraction. We need a common denominator, so 4a squared over 4. Combine that into one fraction, and a couple of steps there with the expansion of a squared minus 1 quantity squared and adding in the other portion. Skipped a couple of algebra steps that you might want to consider. We end up with this fraction a to the 4th plus 2a squared plus 1 all over 4, and that's the left-hand side of our equation. If we then do the algebra to expand the right-hand side, again, not showing the steps, we end up with the same value on the right-hand side. And so we have this sense of the left-hand side is equal to the right-hand side. These numbers are positive, and so we do, in fact, always get a triple, a Pythagorean triple for these values. The question of whether it's primitive, well, one of these values is this odd number. The other two values are separated by 1. And when you have two numbers that are separated by 1, they can't have any common factors unless the two numbers were 1 and 2, and we've already ruled that possibility out just in looking at the values for a that we have available to us. Okay, so what happens is so long as we choose an odd value for a that's bigger than 1, we can generate a primitive Pythagorean triple. So the question is, does this generate all the primitive triples? So all the triples that we are able to generate using this procedure have an odd smallest value, and then they all have two consecutive values. So we have an odd A, and then B and C are separated by 1. So the question is, can we find a triple that does not satisfy one or both of these conditions? So can we find a triple that has an even smallest value? Or can we find a triple that does not have two consecutive values, or maybe and in that case, right? We could have anytime we violate either of those or both of those, that would mean that we would have a primitive triple that does not fit this generation procedure. So pause the video and see if you can create a primitive Pythagorean triple that does not satisfy these conditions. There are lots of possibilities, but a small possibility is 8, 15, 17. So the smallest value is even, and the other two values are a distance of 2 apart rather than being consecutive values. And so what this means is that our procedure that we've developed based on the two initial Pythagorean triples that we met before, that it generates primitive triples, but not all primitive triples. So there is a way to generate all primitive triples based on a formula accredited to Euclid, so again, another ancient Greek mathematician. And this general pattern for primitive Pythagorean triples, I'm going to describe the pseudocode for this process. So we could see this by looking at lots more examples of primitive triples, creating some by hand, and looking further deeper into those and finding other patterns. But our point here is to write down the steps and then convert those steps into Python code so that we can run the code and generate these triples without necessarily at this point deriving the algorithm. We're using the algorithm. So the process involves two positive integers, m and n. The way we choose these integers, m has to be bigger than n. Exactly one of those two must be even, and there can be no common divisor between the two other than 1. So they're positive integers. They are relatively prime is the meaning of that last statement. They don't have to be prime numbers themselves, but when we compare them to each other, they have no common divisors. So once we have chosen these two values, m and n, we set the value of a to be m squared minus n squared. And so we see that the reason for m being bigger than n is m squared then is bigger than n squared, and so a is a positive number. A has to be positive to be a valid Pythagorean triple. So we need that condition of m being bigger than n. We then set the value of b to be 2 times m times n. The construction of these two values, sometimes depending on the m and n, may have a being the smaller of the two, and with different choices of m and n, a may be the larger of the two. So if a is larger, we can reorder so that a is the smaller value. So we just change the names and say, here's a, it's the smaller of the two, b is the larger of the two. And then we can calculate c, and c is m squared plus n squared. And so with these particular values in place, it turns out that if we output a, b, c, that now we have always created a primitive Pythagorean triple. Now we're going to check this to make sure that we are creating primitive triples. But the idea of these values, we can confirm that they are all positive integers. M and n were positive, they were integers, so all of these calculations yield positive integers. The common divisors between a, b, c, again, we can confirm. We're not going to do that mathematically, but we can confirm that these numbers are all they all satisfy the condition of no common divisors, and then the other portion being that these values do satisfy the equation a squared plus b squared equals c squared. Now it turns out that there are some Pythagorean triples that this formula doesn't pick up. It is only generating, of course, the primitive triples. And so when we want to generate all Pythagorean triples, we need to modify that procedure just a little bit. So the new modified version will be able to generate all Pythagorean triples, including the ones that are not primitive. So again, we choose the positive integers m and n, same conditions as before. M is larger than n, exactly one of those two is even, and there are no common divisors greater than 1. But then we're also going to select a positive integer k. And this positive integer k will be used to generate other triples other than just the primitive ones. So we again set the value of a to be m squared minus n squared, and the value of b to 2 times m times n. Reorder them if necessary, and set the value of c to be m squared plus n squared. So all of that is the same. The only difference is that we have created this positive integer k as well. And then at the end, instead of outputting ABC, we output k times A, k times B, and k times C. So the idea is generating all the triples. We create along the way, we create primitive triples and then scale them. So if you notice, for example, the 3, 4, 5 triangle that we started with, a 6, 8, 10 triangle is also a right triangle, right? It also satisfies the Pythagorean relationship. So 6, 8, 10 is not primitive because they're all even, and so they have a common divisor of 2, but they still satisfy the equation, and they are a multiple of a primitive triple. So we have this process of being able to modify the output with a positive integer, we scale these values. So they were positive before and primitive with ABC, and we can scale them if we choose. If we want to generate a primitive triple, we can set k to be 1, and this will generate a primitive triple. So let's look at a Python implementation of this triple generation algorithm. So we're going to need to look at the greatest common divisor. So we're going to use the math module for that. So in our code, let's import math. And then let's create this function called triple that has m and n as parameters and also has k as a parameter. And by default, let's set k to be 1. And we'll see how this works in a bit in terms of what happens when we have this default parameter set. If we choose to change k, we can do that. If we choose not to change k, then by default it will just be 1, so we don't have to say anything. We don't have to tell Python what k is if we want it to be 1. So we'll see this in examples after we have the code written together. Okay, so we're going to look at the docstring first, and we're going to go into more detail with this docstring than we have with other docstrings in the previous examples. So we have our 3 sets of double quotes, and we're not this time just going to do a single line docstring. We're going to do a multi-line docstring that has more detail and more information. And this detail is provided so that the users can see what is really going on. If they're going to use this function and they're not sure how to use it, the information from the docstring is available and will tell them exactly what they need to input and what they are going to expect as output. All right, so we still have our first sentence, this action sentence, output a Pythagorean triple. We could have more detail if we need, if we're thinking that, oh, our users aren't going to know what a Pythagorean triple is. There could be a little bit of description here of what to expect, but we're going to output a Pythagorean triple, and then we're going to describe what the parameters are. Often we will list one parameter per line, but with m and n, there's a connection between these parameters, so we're going to describe them at the same time. They're both positive integers. M has to be bigger than n, and the greatest common divisor has to be 1. And then in addition to that, we said that we need exactly one of m or n to be an even number. So we're describing to the user, here's what you're looking for, here's what these values need to be. And then we have the parameter k, which is just a positive integer. And then we're going to describe what we return. We're going to return a Pythagorean triple, but we're describing it. It's being returned as a 3-tuple, ABC, with a less than b less than c. And in addition, we have that condition or that result that a squared plus b squared is going to be equal to c squared. So if we wanted to say that, we could say that in that return line as well. And then we go to the next line and add the 3 sets of double quotes to end the docstring. So all of this is information that we're going to see is useful to end users, or the end user is sometimes ourselves. At a later point in time, we're using this function and we say, what does this function do? I don't remember what I wrote. What is it for? What's its purpose? Oh, here's what it does. Here's what it takes in as input. Here's what it gives back as output. Now, it doesn't tell you how it does these calculations in the docstring. It tells you what comes in and what goes out. All right, so now what we're going to do is we're going to add in a bunch of error handling to make sure that the user has given us the values that fit what we need them to be. So one thing that we need is we need all these values, m, n, and k, to be integers. So there's a function built in Python called isInstance. And we can use isInstance to check to see if something is a particular data type. Now it has some more abilities beyond just checking single data types, so we're going to use this function in lots of other ways in future. But for right now, let's look at what we have. We want to check to see, is m an integer? So isInstance m comma int. We want to check to see whether n is an integer, and we want to check to see whether k is an integer. If all three are integers, then no problem, we want to move on. But if any one of them is not an integer, then this AND relationship will, the value will be false, and so if any one of these is not an integer, then the part that's inside the brackets is false, and so not that is true. So what this line is saying is we're going to do something if any one of these is not an integer. And the thing that we're going to do is we're going to raise a type error. We're going to tell the user that they have to give us integers. And we're going to specify positive integers just to give them a heads up in case, say, the user put in negative 1.2 for a value. Rather than just saying you need integers, we're going to go ahead and emphasize, hey, you need positive integers, so that if they did make another mistake as well, that they will, at least on the second attempt, put in positive integers. Okay, but that's not the only condition that we have. We need these numbers to all be positive, and int doesn't check for positiveness. So what we're going to check to see is if any one of these values is 0 or negative, so m less than or equal to 0, or n less than or equal to 0, or k less than or equal to 0. So if any of these are not positive, then we're going to raise a different kind of error. This one is a value error. We already got past the test for an int, so they have given us integers, but they may have given us something that doesn't work, and so we are in terms of not working by being a negative value, right? It's an integer, but it's negative, so we have to check that as well. So one line to check for integer. Now we have another line to make sure things are positive. If they're not positive, we're going to raise a value error rather than a type error this time, because the type is fine, it's an int, but the value is incorrect. It's 0 or negative. We want m to be bigger than n. We're looking at our conditions here. M must be bigger than n. So if it's not, if it's less than or equal to, then that's another value error. We say the first input must be larger than the second. Right? So it's a different error that was made. We had integers, they were all positive, but m was too small if we get to this point. Okay, but if we get past all these, that means we do have integers, they are all positive, and m is bigger than n. So in continuing then with the implementation, we want to check the next situation. The next condition is that the common divisor is, we want it to be 1. So if it's not 1, and this is where the GCD function that's in the math module comes into play. This is why we imported math. We say if the common divisor, the greatest common divisor between these, is not 1, then we're going to raise another value error, but it's a different kind of error. And we will tell the user these first two cannot have a common factor larger than 1. All right, so now we are through most of the conditions. The other condition that's left is that we need m and n for one of them to be even, but the other one must be odd. And so there's maybe a couple of ways we could check this condition, but one way is if you think about adding two even numbers together, you will always get an even answer. Add two odd numbers together, you will always get an odd answer, or excuse me, an even answer as well. So add two evens, you get even. Add two odds, you get even. But if you add one of each, you get odd. So the idea here is let's add the two values together, and then using the modulus operator, let's see if the sum was even. If the sum was even, then that means that either both values were even or both values were odd. So we will raise a value error at that point. If the modulus is 1, that means that one of the numbers was even, the other one was odd, and we don't care which one was even or odd, we just need one of them to be even and the other one to be odd. And so this test here says, all right, if both values were even, that's a problem. If both values are odd, that's a problem. And so this test picks up that error. All right, so now we are ready to do the assignment. We've done all of our error handling. We've tested everything, the input that came in from the user. And so we calculate A, we calculate B, and I'm going to go in a slightly different order from the pseudocode and go ahead and calculate C so that we have these values. We have A, B, and C. But we really do need to do the test that says, are they in the correct order? C will be the largest of these at this point because of the way we've done the testing before. The values are appropriate, but A and B may be in the wrong order. So if A and B are in the wrong order, if A is larger than B, we want to swap those two. And there are a couple of ways to swap, but the way we're going to swap is a built-in Python way of swapping, and this is a simultaneous assignment process. We're going to say the values that were in A and B, let's replace those with the values that were in B and A. Now there's some things that happen behind the scenes in this simultaneous assignment, and we will talk about later. But what this does is gives us a way to swap the values in Python without thinking about what happens in memory behind the scenes. But as I said, we'll talk more about that process a little bit later. But what this does is the value for A gets the old value for B, and the new value of A becomes, again, the old value of B. What we can't do in this situation is say, all right, we want to swap them, so let's set A to B and then B to A. So A equals B, B equals A. What that would do would be end up with both of them having the same value. Because if we set A equals B and then set B equals A, well, we've lost what the old value of A was. But this procedure with the simultaneous assignment keeps the old value around long enough to make this transition. And again, as I said, we'll talk more about this later. All right, so what do we have? We have A, B, and C, and they're ordered correctly now. If A were bigger than B, we've swapped them around. So A is less than B, B is less than C. And so we're almost ready to return our Pythagorean triple. Except, again, in that last line of the triple, we're going to return K times A, K times B, and K times C. So what this does is always records the appropriate value. The triple that we end up with is a Pythagorean triple. If K is bigger than 1, it's not primitive, but if K is 1, this is guaranteed to be primitive. All right, so now we're going to have a test to check to see if a given triple is primitive. So if we create a triple, we can check to see if it's primitive, or if we have an output from our triple function, we can check to see whether it's primitive. All right, so let's create a function, and let's call it isPrimitive. And our parameter, let's say, is a Pythagorean triple. We'll just call it Pyth triple. I guess this slightly violates one of the Python kind of suggestions of the length of names, but it's not too long and it's descriptive enough. All right, so again, we're going to have our docstring, but this time we're going to have a one-line docstring because this function is going to be a Boolean function. It's going to return true if the input is a Pythagorean triple and false otherwise. Now the triple that we're looking at, triples come in the form, we said triples are tuples, they are 3 tuples, and so we need the input to be a 3 tuple of positive integers, and so we're going to go through and return false if anything goes wrong, if anything is not completely appropriate. So if the thing that is input into our function, if the argument that we get is not a tuple, so we're using is instance again, if it's not a tuple, or if it is a tuple and the length is not 3, then we have bad data, and so we will just return false. Now in this situation, we're not raising type errors or raising other type of errors, raising any kind of error, because this is a Boolean expression. The only thing that it does is it returns true if everything was perfect, and it returns false if anything went wrong. Doesn't tell you why it returns false, doesn't tell you anything about that. This just gives back true or false. Yes, the thing that you gave me satisfies all the conditions, or no, something went wrong. All right, so now then we're going to start looking at the rest of the conditions. We do have a tuple that has length 3 if we get past this point. And so now what else do we have to have? Each of those values needs to be a positive integer inside there. So we're going to loop through these values and do some extra testing. So at this point, if any one of these is not an integer, or if any of these are not positive, then we will return false, right? There's something that went wrong. We will return false at that point as well. Okay, so going on, we now need to look at the values themselves and do some work with those values. So since we need to do some testing with those, I want to go ahead and do the simultaneous assignment again, and let's set A to be the first value, B to be the second one, and C to be the last value. These are tuples, so we can index. The index values are 0, 1, 2. So let's go ahead and pull the ABC out of the tuple and use those in our calculations. All right, so what calculations do we have to check? We have to check to make sure that all of these have a GCD of 1. They have no common factors bigger than 1. And so if it's not 1, by the way, GCD doesn't just work with 2 values. The GCD function can have more than 2 values, and it checks all of them. Is there anything in common across the board? And so we see that there is nothing in common across the board. And so in this situation, our test is if there is something in common, then we're going to return false. So what we want to have happen is we want the GCD to be 1, but if it's not, we return false. Okay, so what do we have at this point? If we get past the first test, then we do have a 3 tuple. If we get past the second test, then all the values are positive integers. And now if we get past the third test, then all the values have the greatest common factor is 1. So what's left to test? The thing that's left to test is to make sure that this is actually Pythagorean. After we've tested one more piece, which is, are they in the right order? So our triples need to be in order. So we check to see, well, if B is out of order, if B is smaller than A, or C is out of order, it's smaller than A, or if B and C are out of order, C being less than B. If any of these things happen, we return false. So tuples of length 3, positive integers, GCD is appropriate, and they're in the correct order. Then we can check now, finally, the Pythagorean condition. Is A times A plus B times B, is that equal to C times C? Now this time, this is something that we want to have happen. So if we get to this point and this does happen, we return true. But if we get to this point and it doesn't happen, then we return false. So the order that we chose for doing these tests is kind of in the sense of the kinds of mistakes people will make and the order that we expect them to make those mistakes. So we expect probably somebody who's using this accidentally gives us something in the wrong format. That's pretty common, so we're going to return false really quickly, and then none of the rest of this gets tested. Well, if they give us in the right format, then maybe they've made a mistake in the values, and so we'll return false again pretty quickly. Then we get deeper testing. These two lines with the GCD and the order, we could do those separately, but the GCD mistake is probably more likely, and so we'll return false if we get to that one. But we get down here to this point, then we say, well, if they did give the correct answer, let's go ahead and tell them, yes, you did fine. This thing is a primitive triple, but if there's still something wrong with the triple they gave us, it will be a triple. It just won't be Pythagorean at that point, right? It's 3 values, they're all positive, and so on. But at the very last step then, if anything at all, anywhere in here goes wrong, we return false at the very end. All right, so this function will then test to see if you give us a 3 tuple, is it a primitive Pythagorean triple? And it has to satisfy all of the conditions in order to get back true, violate any of those conditions at all, and we get back false from this function. Right, so let's see how we can then use this code. We have these two functions, they're in the same file. And so to use this code in idle, we could at the prompt say, type this message, print triple 531. Now at this point we're going to get an error message. And the error message that we're going to get is the one that comes from the fact that M and N, one of those, exactly one of those, needs to be an even number. And so we'll get an error message related to these values are not, they don't satisfy the even odd requirement, right? One being even, the other being odd. All right, if we change the values and we print a triple 651, we'll get out the 3 tuple 11, 60, 61. This is one of those primitive triples that has an odd value, and then the next two values are separated by 1. Well, in this case we used k equals 1, so we could also get the same result if we left the k off the input and just put in 6, 5. The function knows, oh, well, okay, you didn't give me k, so k must be 1. And we get the same tuple at the end. All right, another example. Again, these are all line by line at the prompt in idle, in the shell. If we print triple 10, 3, that's telling, again, k is 1 behind the scenes, and we get another triple. And this triple is one of those that has an even value at the beginning, and the next two values are not separated by 1. So just choosing different values, we can see lots of different Pythagorean triples. All of these will satisfy the condition of, in this case, 60 squared plus 91 squared is equal to 109 squared. You can test that. If we did triple 7, 4, 2, so this passes the conditions. 7 is bigger than 4. One of these is even. Now we have k equals 2, and we see that this time we get a non-primitive result. All of these values are even. But again, you can test and check to see that these are, in fact, they do form a Pythagorean triple. Not primitive, but 66 squared plus 112 squared is equal to 130 squared. All right, so let's try the is primitive function. If we give it the tuple from back here, the 11, 60, 61 tuple, we get back true. That one satisfies all of the conditions. We don't necessarily have to type in the triple ourselves. We can say, hey, let's use the is primitive function, and let's also then call the triple function on 742. So the triple 742, that returns this tuple 66, 112, 130, and then that gets fed into the is primitive function. We just said that wasn't primitive, and so we get back false in that case. All right, what if we put is primitive 11, 60, 61? This says false, but I thought 11, 60, 61 was a primitive triple. What went wrong here? Well, if we look at this, we did not send a 3 tuple to is primitive. We sent 3 separate values to is primitive. The tuple is a single value. Here we had 11, 60, 61. It's a single thing. It's one tuple that has 3 things inside of it, but it's one tuple. And so things have to be in the correct format. Is primitive needs things to be in the correct format. This is not in the correct format, so we get back false. Again, this function doesn't tell us why we got back false. It just tells us something went wrong. And the thing that went wrong was, in this case, incorrect format. In the previous case, the thing that went wrong was the values had a common divisor bigger than 1. And there are other things that we've seen already that is primitive is looking for. So if any one of those goes wrong, we get false. If they all are appropriate, we get back true. So as usual, feel free to ask questions in the comments, by email, or on Discord. And have a great day.